we are getting into some more advanced optimization related input-output territory here. We're gonna be doing some scattering, some gathering. We're gonna figure out what this V at the end of read and write stands for. We're gonna look at how this is used by some big boys. We're going to have a lot of fun. Okay, so let's clear this out and change the size back. And let's imagine you have a PNG file that you want to read and maybe parse, and for some reason you want to have the PNG header to be referred separately from the data itself. So how are you going to do it with traditional code? So you would of course need some basic includes. So let's include std lib.h, what another one, std io. You would need your main, the regular stuff. And here, so first of all, you would open, of course, the file, which is, this should be double quotes, this.png. So let's actually probably open a manual for open. I'm gonna use a raw system call, not any libc wrappers. We are going to need, of course, its include and its path, and then flags and optional mode. So flag is something like read only. So it's, yes, this one, o_rd only. So o_rd only. So we will need to open our file, then we will need to figure out the file size, something, I guess, read file size that we're gonna define. After that, we need the buffer that we're gonna read the file to. So character star buffer equals something, I don't know, malloc with file size, I guess, and it's to be cast to character star, the result of it. And after that, what are we gonna do? We are going to read. So read to this buffer from file descriptor to the buffer file size. Nice. And I guess bytes read. Yeah, right. So because we probably want to check if we read everything correctly. So after that, let's, I guess, print some red. We're gonna have some debug output. So bytes read, file size. Yeah, we also need, of course, some header age equals to, we need to point it to at the start of the buffer, right? So we read the entire file to the buffer, and then the PNG header is at the very start of the file. And I guess it's gonna be a pointer to header, something like that. Okay, where do we get a file size? Let's define that. It's gonna return an integer, I guess, and it's gonna accept int fd file descriptor, right? Because we already have it. Let's, I guess, provide it here. And how do you get file size from file descriptor? Well, you use fstat. Yeah, this is the one that you can provide a file descriptor and a struct that is a stat buff. So it is sb stat buff, and it's struct. You need to prefix it because it's not type def as far as I remember. After that, you just call fstat with fd and address of sb and int result, right? Let's check if error, if result. I think it should be a 0 if it's all correct. Let me quickly check it out. Yeah, on success, a 0 is returned. Yeah, so just print fstat error. I'm not gonna really bother with a particular error. And after that, we need to return the file size. There are different types of files on Linux, and I'm gonna be only concerned with regular files. And fstat manual here, it should have an example. There it is. So we check on SB, yeah, SB st mode with some mask. So let's just straight up copy paste here. If this and if it equals is reg, so reg means regular file, and if that's the case, we just return sb, the size is st size. There you go. Yeah, so manual for Linux syscalls is usually pretty good. Feel free to use it. Next, we need to define the header of our PNG file. So struct, I'm gonna type def it because I like it like that. So header def, again, if you don't know C, so you do this type def, so you don't have to prefix your variable declaration with struct. You can just do header H. Yeah, that's literally all there is to it. And to get the structure of the header, let's refer to Wikipedia page that I have opened on the site. Here we have a file header format. So a PNG file starts with 8-byte signature. Nice. Let's copy its format and paste here. So, and we start with 89, which is a literal byte. So let's just call it uint 8_t en. So 89, I'm gonna use stdint.h. So let's include it. Include stdint.h. After that, we have 54E47, letters PNG literally in ASCII, so character PNG, so it's 3 characters. After that, DOS style line ending, CRLF, so char CRLF, which is 2 characters. After that, 1A, which is end of file character, uint 8_t e off. And after that, we have OA, which is end of line on Unix systems. So character F1, 1 character. And there shouldn't be any weird paddings because this is literally just 8 bytes. So 1, 2, 3, 4, 5, 6, 7, 8. Nice. So there should be it for PNG header. And there is absolutely no way I got it the first try. So let's gcc main.c, let's compile it. Storage size of stat_buff isn't known. fstat is not declared, so I know that. I just need to include the right header for stat. There you go. Stat_buff, I guess it's gonna be declared here. Also, I just realized I mixed those up. Let me recompile it like that, so you can see what's going on. Read is not declared because I need to include unistd.h. Again, let's compile it. And oh wait, why is it stat_buff? It shouldn't be stat_buff. So again, let me open fstat. It is stat. So struct stat is a type. This is the name of the variable. Yeah, I just skimmed it too fast. And now it compiles. So let me run it. File size this, and read the same file. And I guess for an extra foolproofness, let me print the struct. So let's print f%x_struct. So we need h, we need to cast it to a pointer to uint64t. So basically I want to print header as hex so we can compare all the numbers. A pointer to this, and then I need to dereference it. And I think, yeah, as soon as I get the syntax correctly, 89 is correct. So I'm reading it right to left because we're dealing with little endian, of course. So 89, so 54E47, which is right. And then, it only printed the first half because I need to do it like LL, like this. So I print all 64 bits of it. And yeah, there you go. Then we have, so 47, then we have 0D, 0A. So 0D, 0A, then 1A, 0A. So 1A and A. There is a leading 0 that we can fix by prefixing this with, I think it's 016. And yeah, printf formatting is kind of weird. You just need to know these incantations. But yeah, here it is. Nice. So we got the header correctly. All right, now you have an entire buffer that has all of the PNG file in it. You have a header at the start and then an actual data, which we, I guess, can call payload. So void star payload equals to, I don't know, like buff plus size of header, right? Then you have this payload, and in order to parse an actual PNG, you just send this payload into some parsing function. This is pretty typical. I think everybody understands what's going on here, and it's not that bad. We only need to do a little bit of math, right? We need to offset the payload from the header, and we then can do something like payload size equals to file size minus size of header, and then I guess we send both of these to a parsing function because that's how you do it in C. But imagine if you have a binary format that has something like a header with a count at the start, and then it has a count amount of things that you need to parse, and maybe you want to slice them off into separate buffers so that then you can pass these buffers into like parallel parsing functions. It can be like an arena per thread or something like that. You can imagine different use cases. So what I want to say is that there is a family of functions that automate some of this while at the same time saving on syscalls, which is always great. So let's look at manual for readv. It says read or write data into multiple buffers. What does it mean? So if we look at the signature, we will see that together with the file descriptor, it accepts an array of iovec structs, iov and the count. What are those structs? How do they look like? Essentially, iovec is a struct of something, I think it's called iobase, a void pointer, and a size t. That's literally all there is to it. If you saw any modern programming language that has a string type, this is literally it. A pointer to some buffer and the length in bytes of that buffer. readv accepts an array of these. And you can probably already imagine where we are going. So readv will take buffers that are not necessarily contiguous in memory, and it will read the file into these buffers depending on how big these buffers are. And that's where the terminology comes from. So first, v at the end of read stands for vector, where vector here is in the same meaning as std vector in C++. So it's just a buffer with a count. So that's your vector. And the process of reading into buffers that are not contiguous in memory is called scatter. So buffers are scattered in memory. Also, that's literally all there is to it. readv scatters the content of the file into these vectors, so buffers. Okay, let's see how it looks in the code. So first of all, let me remove the definition. Let me include the uio.h somewhere probably here. And let's write the code. Instead of allocating the buffer with an entire file size, we need to allocate it as file size minus size of vector. So size of, not vector, sorry, header, because header will be stored separately. And we can just literally here, let's, I guess, comment this out as well. So, and the header, we can just store it on the stack. So header h. Then we need to prepare the array of these iovec structs. So it's going to be iovec io, two of them. And then the io 0 will be our header. So io of base equals to address of h. And io of len is going to be what? Size of header. Then, sorry, this is going to be 0, this is going to be 1 and 1. And this is base, yes. So the second base is going to be our buffer. So this is where we're going to read the payload of the file. And the length is going to be a file size minus size of header. And then what we'll do is, so we don't need any of this, we don't need that. What we're going to do is int bytes read equals to read v. We provide fd, we provide io, and the count of io is 2. And that should literally be it if I did everything correctly. All right, let's try to compile it and look at the errors. Unknown type iovec. Yes, it's because let's just type def it. Type def struct this to this, because I just can't be bothered. Again, let's compile it. Printf cannot convert to a pointer type. Oh yeah, because it is already on the stack, so like that. And that's it. So, okay, it seems to be working. Again, we have our signature. It starts with 89 and ends with 08, 0A, 1A, 0A, yeah. So this is all correct. The functionality is totally the same. And you can see the file size and read size is the same at the end. So readv also returns the amount of bytes read, not the length of this. But notice that header is now stored completely separately from the payload itself, right? So payload is pointed at the buffer. And now this buffer contains just the file itself that we can send out in our parsing function. We can probably even send it as iovec if that function accepts something like that. So this is readv. Now, what about its counterpart, writev? So the easiest way to demonstrate it would be something like logging. So let's say we need to log message with, I don't know, system has failed. Something like this. Let's imagine we get this message from some third party we have no control over. And let's declare this function. So it's going to be void log msg, and it's gonna accept character star message, and it's going to additionally log, let's say, a timestamp. Character star, we need the time as a string, now equals to, we're gonna use ctime, I guess. And ctime accepts, let me look at it, ctime. So yeah, first of all, let's include its header, time.h, and ctime accepts this, so time t. Struct time t t. Actually, I think you can just use that, time t, so it accepts an address of these and accepts that. And at the end, we also need to append the end line, because our third-party function that returns this log doesn't have end of line at the end, and we need to write it to a log file so that we can then write a next log line. Makes sense. And also we will need to chop an end line from now, because ctime actually returns the time with the line ending at the end, which is slightly annoying. Okay, so how do we achieve it? Well, we get now length, which is str_len of now. Then we calculate the entire log size, which is okay, it's an integer, str, so it's now length -1 plus str_len of message, and +1, so the resulting line ending. Actually, well, first of all, this is the correct. We're not gonna do -1. We are going to use entire now length, because we're gonna substitute end of line with the white space. Yeah, so this is our entire log size. After that, we need to allocate the buffer for our log message, because we need to write entire buffer all at once with write syscall. Otherwise, you can imagine in some sort of multi-threading logging, if we write chunk by chunk, the stuff will get interleaved and our log will make absolutely zero sense. So yeah, character star malloc of log size. After that, we need to memcopy our chunks into our buffer, right? So memcopy into log buff, and memcopy accepts destination as its first thing. So now, and now length -1. So we copy everything, but without the line end, and it's length like that. After that, we copy a single white space, but it's gonna be log buffer plus now length -1. Is it length or is it, because I keep messing it up? So it's, yeah, it is length. I don't know why I keep messing it up, probably because it's almost 3 a.m. and my muscle memory plays tricks on me. So now length -1, we copy a single white space and the size is 1. After that, we copy message and str_len of message. And after that, so log buff, log size -1, we just append end of the line. Sounds good to me. Now we need to open the file for writing. We use open syscall, and the path is log.txt. We need to open it for writing, and I remember it's rdwr, and there is some other we need to provide to create. I actually remember it's all create, it's all in the manual. And then here we need a mode so that the user can actually write into it. Let me refresh my memory, open. It's something like, yeah, there it is. We need 600, so we need these two is user. User has read permission, so we need to mask, we need to order this one and this one together. That should be it. Unix world is allergic to vowels. And after that, we just call write on this file descriptor, so logfd. log buff and log size. That should honestly be it. Let's see if it actually worked. So gcc main.c, and of course it's not strlen. I need to include string.h. Include string.h, and now it works. Let me call and log. Oh, okay, so Saturday we have a white space after the time system has failed. Let me actually check if there is a line end at the end. So let me open the log, and yeah, here you can see Max shows us that there is a line ending at the end. So yeah, all good. Our log message works. Now, how will you write this with using readv? Let's actually copy and paste this entire thing. Let's call it log message 2, and it's gonna have time t, it's gonna have our now and length, but we don't need to create a uniform buffer anymore. As you have probably guessed it already, a readv, so this is how it's gonna be at the end, readv, we're gonna accept another array of vectors. And so instead of doing all of this, let's actually prepare our IO back. IO of is gonna be 4, right? So the time, then the white space, then the message, then the end line. And then IO, the first one of base, it's gonna point to now, and its length, it's gonna be now length -1, because we want to chop the line ending. Now the first one is gonna point to message, and the size is gonna be to strlen of msg, but actually not. Actually, this is gonna be the second one. The first one is gonna be a white space, so instead of a line end. And how do we organize it? Let's do something like spaces to, so it's gonna be white space and line end, and we're gonna take both from here. So it's gonna point to spaces at the very start of the buffer, and it's gonna be a length of 1. And this actually will show a nice property of these arrays, is that they literally don't care where to take their memory from. So the white space will gonna point at the start of this buffer, and then end of line will gonna point at the end of this buffer, and the kernel will gonna treat them separately. So then we take the third one is going to be the end of line. So it's gonna be spaces +1, and the length is gonna be 1. And then our right, we're gonna take this and 4 of them, and let's change this to log msg2, and let's remove log.txt and recompile the file. Actually compiled first try, kind of sus a little bit, but yeah, let's ls, there is no log file, and then let's a that out, and let's see if there is a log. There it is, and we have our line ending, and we have our, oh, actually the timestamp is wrong all of a sudden. And I am going to be absolutely cooked for this in the comments, but honestly, very deserved. So I'm gonna leave this in the recording. So what happened there is that I did not initialize this variable, of course. You need to pull time with it. And I literally just recorded a video about why uninitialized variables are so dangerous and see 2 weeks ago. And here I am getting wrecked by it. But yeah, we need to initialize the time t. Actually, I probably had the same exact issue in log msg, the regular one. I just haven't paid attention to what the timestamp actually said. But yeah, here I initialized the time, then I passed this t here, and now if I remove the log file and recompile and run it, now the log, yeah, here you go. Now the log shows an actual date, an actual timestamp. It is actually 3 AM. So please don't judge, or judge, actually judge. I deserve this. You need to initialize your variables. But right, what about readv? Here in the first log message, we created a big buffer and then accumulated everything into that buffer. We had to mem copy everything in and then write, because otherwise the writes would not be atomic. The readv, on the other hand, accepts scattered buffers, and what it does is it gathers them together. So this is where gather terminology comes from. it takes buffers that not necessarily contiguous in memory and it gathers them together in a single write call, and you don't need to do any mem copies. It does all of this for you. And even more than that, it does it atomically. It does it atomically in a way that if you have this file descriptor shared between processes and between threads, nothing will get interleaved, so you can freely dump log in the file and not worry about anything. Well, actually, it's not quite correct. This thing is atomic in a sense of being quote-unquote thread safe, but if your program crashes, then your writes can get weird. Or if you get a power outage. But you know what modern Linux kernel has? I actually only learned about it when I was researching for this video. And so if you read a man2p write v2, so this is a function from the same family, so it's also readv, and it has a flag that's rwf atomic. So this is the one, and it exists since Linux 6.11, so it's just not even 2 years ago. Look at this. Requires that writes to regular files in block-based file systems be issued with a torn write protection, where torn write protection means that for a power or any other hardware failure, all or none of the data from the write will be stored. That's crazy. We get here into a territory of like write-ahead logs in relational database management systems. Whether this is something that should be done by a kernel, I guess is an exercise for the reader. But yeah, Linux kernel is very, very powerful. But since we are here, what does p means? And before we go there, yeah, this is very cool. This is kind of like a cute functionality, but you might say like, it's kind of niche. Mem copies are extremely fast and all the people use arenas now, so you will have like a buffer where you will read the entire file, and I don't know if I really want this. And you're kind of right. I don't know if a lot of people would use a regular writev or readv as much, but there are a lot of enhanced versions of this functionality. In fact, there is entire family of syscalls that operate on this vectorized input, so to say. And one of them is readv with a p at the start, so preadv. The preadv system call combines the functionality of readv and pread. So it provides a fourth argument offset. So this is kind of more enhanced. And then there is preadv2, which adds a bunch of flags. And those ones, so there, you have it here. So there's like a bunch of flags. And these are actually very useful. In fact, I've checked that PostgreSQL, so I think there's Postgres, it actually uses preadv in its source code. So of course it has a bunch of optimizations, but yeah, it just plain uses preadv. And also you can notice something here. It has IOUring code path, and IOUring also operates on this IO vector. It has a submission queue where you can set up readvs, and you also pass there an array of these vectorized inputs. So what I want to say is that even though a regular readv and writev might not be as impressive, there is an entire family of this functionality. The concept itself is very useful. People really want to save on syscalls. And I guess the final boss of this concept on Linux is IOUring. Actually, at first I wanted to do IOUring video instead of this one, but then I thought that it would be very, very loaded. So I decided to do a video on this vector IO first. And let me know if you want some IOUring content. And in fact, this concept is actually so useful that Win32 API has exactly the same functionality. So it has write file gather that accepts a handle to a file, and the segment array, which is our vector structs. And also it has read file scatter. So there you go. So the same exact thing as readv, also that accepts a segment array. So yeah, what I want to say is that this concept is not Unix exclusive. It's just generally very useful stuff. But yes, now that we got ourselves familiar with the functionality, we looked at it, let's look at something else. You might have noticed that I have a Wayland directory here. This is a Git clone of FreeDesktop's Wayland repository, straight from their GitLab. It has libwayland source code in it, and libwayland is the cornerstone of all things Wayland. Pretty much all important Wayland programs use it, and inside it has a file called connection.c, which contains a code of implementation of Wayland protocol's binary format. This code is about 1,500 lines of code, but it actually uses this concept of vectorized input-output in a very clever way that I wanted to show you. At the core of it is Wayland connection structure. Here it is. It has 4 ring buffers and some other craft we don't care about. And ring buffers are for incoming and outgoing Wayland messages and for passing file descriptors in and out. And the ring buffer itself is here. It has your regular pointer to an actual data and head and a tail of the ring buffer, as well as size and capacity. If you've never seen ring buffer before, just briefly, it's a very straightforward data structure. You have an array of bytes and 2 points in it, head and a tail. So head and a tail. And there are usually, let's say, 2 parties that participate in a ring buffer. Somebody puts the data in and somebody else reads the data out. And the occupied data is usually between the head and the tail. So at the very start, when the buffer is empty, both head and tail are here. So let me actually simulate it. So both head and tail are here at the start of the buffer. Then somebody comes in and puts some data and they bump the head. So head actually goes to here. And then this data is considered to be occupied. And this data, this one is the free space of the ring buffer. Now somebody else comes in and tries to read the data and they bump the tail towards the head. And this goes on and on until one of them or both of them arrive here at the end of the buffer, in which case there is some sort of simple modular magic that wraps the point back around. And it goes on and on from the start, hence the name, the ring. Hopefully it makes sense. And let's say there is an outgoing Wayland message, so somebody puts this message into an out ring buffer and then wants to send it to the receiver, in which case we have connection flash function that does this logic. So it accepts the connection and at the start it puts 2 our IO vec structs on the stack. And then here is the loop that checks if there is still something to send out. And we're not gonna look at this code path. It prepares a file descriptors, we don't care about it. Here, if we need to send an actual message, it actually calls a function that's called ring buffer get IOV. And it passes the out ring buffer as well as our structure. So let's take a look at it. Here it is. So first it gets head and tail of the buffer and then it checks for 3 possible cases. First one is tail is less than head. So in our case, it's the situation where here's the head, here's the tail. So there is a data to be taken off here. And in this case, we only need 1 IOV struct because we can just take this contiguous chunk of memory and point it to our struct and say that count is 0. So second is if head is 0. So for example, if head was somewhere here, it wrapped around and now the head is here and the tail is maybe somewhere here, which means that the occupied data is stored between the tail and the head. So here's the occupied data. In this case, it's also contiguous and we can just put put our IOV base to it. And also we only need one IOV extract. But the third case is actually more interesting. It's when tail is head of head. So this actually means, so let's say this is the tail and head is maybe somewhere here, right? So this is the head. It means that the data is laid out partially here and partially here, right? So our data is torn apart between this part of the ring buffer and this part of the ring buffer. In this case, we need both of our IOV struct. So first of them will point to this chunk of data, and the second one will point to this wrapped around chunk of data, and the count will be 2 of them. And so after that, there is a struct called MSG where we put our IOV struct as well as their count. And at the end, it's going out with send MSG. So what is send MSG? So send MSG is send message. And if we check its manual, man to send MSG, send a message on a socket. It operates on, on a socket, and it accepts a struct MSG SGR, which stands for message header. And this struct, here it is, it takes an array of IO vectors. So scatter and gather array. It uses exactly the same concept. So this send message is one of the vector family, you can call it this. Here, libwayland uses this clever trick where it only needs one ring buffer for consumer and producer. And if a data is partially torn apart between the end and the beginning of the ring buffer, it just puts it to 2 different IO vecs and atomically sends it through the socket. And for the receiver, both of them appear as a unified stream. So the receiver doesn't see any torn state. It can just receive this buffer as a whole. I think this is a very clever trick, and it totally avoids unnecessary mem move calls. All you need to do is very cheap modular math to correctly calculate the wraparound. And for the receiving end, it's exactly the same thing. So here's our IO vec structs, and again, there is some kind of a loop, while true, dangerous. So again, we call ring buffer put IOV. So this is the same kind of thing. Again, some ring buffer magic. If there is a torn memory, we use both of our chunks of the ring buffer. And after that, we again prepare our control message struct, and we call readv MSG. So this is like receive message. Exactly the same thing, but instead of sending the message, it receives the message into potentially scattered buffer. So yeah, I was actually reading libwayland code because I wanted to know more about Wayland, so naturally go read the reference implementation. And I've found this very cool and clever case of using ring buffers together with vector IO, and I just was so hyped. I also wanted to add it to this video. This is gonna be it for today's session. Hope I got you excited about more advanced IO patterns on modern operating systems. Feel free to cook me in the comments for all the mistakes. Subscribe if you liked what you see. Let me know if you want to watch a video about IO U-ring, and I guess I'll see you next time. Hopefully no more home directory situations.